Right. So we were discussing about superposition of waves, and we saw the second type of superposition of transverse waves, when waves traveling in opposite direction but with same frequency and same amplitude are superimposed. Then we have what is called the stationary or standing wave. Okay. So quick recap. So what we saw that we have waves of this type. Stationary or standing waves. The example of this we have taken is those created by superposition. So in the case of course, we are still in the domain of transverse waves. Because all these phenomena we are seeing in case of transverse waves right now, we will see the similar phenomena, but in the case of longitudinal and electromagnetic waves later also. So anyway, so we have one wave traveling like this of frequency f and amplitude e. And we have another wave traveling in the opposite direction, frequency f and same amplitude. So their superposition we saw, that results in standing waves. So suppose my y1 is e sine omega t minus kx, and y2 is t sine omega t plus kx plus phi, some space constant phi. Then the resultant superposition of y1 plus y2, that becomes 2a sine. In this case, it will become omega t plus pi by 2 cos kx plus pi by 2. In this particular case, because I have taken the phase constant to be pi, or the phase difference to be pi between these. So this becomes what we call a stationary wave, because we can see the amplitude of displacement at any point is position dependent. You can think of this as, the modulus of this term becomes an amplitude, whereas the angular frequency term is like this. So this becomes the general equation you can see in this case of standing or a stationary wave. Now we'll study some more properties of this before moving on to stationary waves created by vibrations of a string, which is of finite length and between two types of boundaries. So that will be more or less the main thing we'll discuss today. I know that there might be some doubts and all pending from the assignments I've set, but I will keep some time aside for that separately. And let us finish this theory part today. Because in that, by completing this theory part today, first of all, you will be in a position to complete remaining questions of transverse wave chapters. So that now gradually we can also get into the next chapter from the next lecture, the sound waves, etc. So I will start with the theory thing, and we keep some time for discussion of doubts and things like that. Yeah, so now coming to this, we had already seen the property of this, that so at any point x equal to x, or for a particle at x equal to x on the string, the amplitude of oscillation was mod of 2a cos kx plus phi by 2. So we saw that the amplitude becomes variable over here. So we saw, therefore, the amplitude of oscillation is position dependent, and it varies between a maximum of 2a and a minimum of 0. So we saw that in the case of standing waves, we have what we call position dependent amplitude. And where the amplitude is maximum, such points are called nodes. Sorry, they are called anti-nodes. So specifically, there is a and these sort of points where the amplitude is 0, they are called nodes. We also saw that the if you superimpose the what we call the snapshot pictures, as the wave evolves with time, the snapshot pictures evolve in this way. And after some time, like this, then after some time it's back to this blue colored line, then it's back to the flat line, then it goes to this kind of position. And then further after some time it goes to this kind of position. So in this diagram you can see that these points, they become the antinodes, where the amplitude is maximum. And we had seen by calculation that the distance between two consecutive antinodes is lambda by 2. Lambda by 2 is the same thing as pi by k, because 2 pi by k was lambda. And these type of points, they are called the nodes. These type of points here have zero displacement. And again, that is also symmetric in the same manner. The distance between consecutive nodes is also lambda by 2. Okay. Of course, in terms of the x coordinate of the node and antinode, where they are located, that depends on that phase constant phi. Or the amplitude term, it was cos kx plus phi by 2. So it depends on what that phi is. Okay. But for example, in the special case where phi is 0, your nodes are at x equal to 0, lambda by 2, lambda 3, lambda by 2, etc. Because those are the positions where cos kx, sorry, your antinodes are. Those are the positions where cos kx is either 1 or minus 1. Whereas your antinodes is where cos kx would be 0. So that is, kx should be equal to pi by 2, 3 pi by 2, and so on and so forth. So x should be equal to lambda by 4, 3 lambda by 4, and so on and so forth. Okay, so that's something we've already seen. So just completing this thing about the geometrical properties of this, seeing that this is lambda by 4. So a particular node and the next consecutive antinode, or a particular antinode and the next consecutive node, they are always spaced out at lambda by 4. Well, lambda by 4 is exactly half of this. Okay. So these are things that we've already seen, the spacing between the nodes and antinodes, etc. Now, a few more things to understand about the physical properties of this. Okay. So as far as this thing is concerned, the oscillation is concerned, we've seen about the amplitude. Okay. All medium particles oscillate, of course, other than those at the nodes. Precisely the particle which is at the node, they will experience complete rest, always in a state of rest. So other than that, all medium particles oscillate with common frequency, omega by 2 pi. Okay, and variable amplitude. Okay. But such that if you're talking about the phase of oscillation, okay. Now, if you look at the position of the string between two consecutive nodes, so if you look at all the particles between these two, they will be evolving with time like this. So you can see that at a particular instant of time, all these particles will be here, for example. Then at a later instant of time, all these particles will be here when they reach the maximum displacement. The particle velocity would be zero. But for example, before reaching the maximum displacement, the particle velocity will be like this for all of them. So at some particular instant, the particle velocity is non-zero. Now, if you compare them with the particles which are between the next two consecutive nodes, so also compare those particles between the first and the second node over there to the particles which are between the second and third node. So they are, oscillating like this as time is progressing. So at a particular instant of time, if this set of particles was here at some t equal to t1, let's say, then these set will be somewhere over here. And then at a different time, when those particles between the first and second node have reached their displacement maxima, okay, the particles between second and third have also simultaneously reached the displacement maximum, but they've reached the maximum displacement on the negative side. So their Vp is 0. Okay. So for example, if I consider two particles here, x1, x2, and also two particles here, x3, x4, you can see the pair of particles x1 and x2, regardless of what exactly their amplitude is and regardless of where exactly their position is, but they are just 2 points which are between the same consecutive two nodes, so they will oscillate in phase. So if you take two particles, any two particles which are between any two nodes, between consecutive nodes, then they will always be oscillating in phase. That means they will reach their positive maxima simultaneously, they will reach back their mean position simultaneously, the negative maximum simultaneously, and so on and so forth. They might be oscillating with, so if you compare x1 and x2, there are two particles like this might reach a different amplitude, this might reach a different amplitude. So this might reach an amplitude of A1, this might reach an amplitude of A2, but they will both be at this position and this position simultaneously. If this reaches here at some t prime, this will also reach here at t prime. Then if this comes back here with a velocity v1, but at some time t double prime, then this particle will also reach here at the same, with a different velocity, but at the same time. So these two particles x1 and x2 will be oscillating in phase. Similarly, x3 and x4 will be oscillating in phase. But if you compare x1 and x3, or you compare x2 and x3, or x2 and x4, two particles which are on opposite sides of the same node, instead of being in between two consecutive nodes, if they are on one particle is on the left and the other particle is on the right, so on opposite sides of a particular node, so any two particles like that, they will be oscillating with a phase difference of pi. So this is the next important thing to understand about the phase of oscillation. So while all medium particles have common frequency and position different amplitudes, so in general different amplitudes, okay. However, all particles situated between two consecutive nodes oscillate in phase. That is, they reach maximum displacement simultaneously, cross their mean positions simultaneously, and so on and so on. Okay. Whereas, so example in the above diagram, x1 and x2 in the figure above, okay, those are two particles which are oscillating in phase, or the particles x3 and x4 which I have drawn above, they are oscillating in phase. Whereas if you, as we were discussing, if you look there is a pair of particles that are situated on either side of a node. Example, x1 and x3, or x2 and x3, or x1 and x4, or x2 and x4. They are oscillating with opposite phase, or a phase difference of pi. And also you will understand from this in general. Now if you consider all the particles here between this and then now the next node, so they are at that particular instant they are like this. So again you can also see that these two particles x1 and x2 will be in phase with any particles between these two, let's say x5 and x6. You can also see that x1 and x5 are in phase as far as the oscillation is concerned. Then, but whereas x3 and x5 are out of phase with a phase difference of pi. So this becomes another important aspect about the standing waves. So I'll just give you a minute to go through this. This is, of course, this part is a review. We were already discussing and we've already seen all these points in the last lecture. But now, a particular importance. What happens to particles which tend to be at the node? The particles which are exactly at the node, so unka kuch displacement ही नहीं हो रहा है. They are remaining at rest. So they are not in oscillation. So there is no point discussing their amplitude and these things. Tending to their amplitude is tending to zero. Okay. But if you take two particles which are nearly at the node but on the same side of the node, they will be oscillating in phase with amplitude tending to zero. Whereas if you take two particles on opposite sides of the same node, they'll be tending to oscillate with a very, very small amplitude tending to zero, but out of phase with a phase difference of pi. So let's come to this part now about the phase difference of various particles. Okay, so hope this point is clear now to all of you. Right, Sudhir, so that point is clear, I hope. Okay, good. Okay, next thing we'll talk about the energy of the standing wave, and this time we'll talk about the total mechanical energy instead of talking about power, because it's not a progressive wave. So it is not transmitting power. In fact, the standing wave, in this case, we have seen the standing wave created by two sources which are creating waves in opposite directions. So the part of the string which is oscillating is the part which is between those two sources. It's a fixed amount of string which is oscillating. Unlike a progressive wave, the extent of the particles which are oscillating is not continuously increasing with time. Because a progressive or traveling wave, is something that is traveling along the string. So as it is traveling, the total number of particles that were oscillating was increasing with time. Your dx by dt was there. So as a result of that, what was happening is that there was a power transmitted. But here it's a fixed number of particles that are oscillating. So it has a fixed amount of energy, the progressive wave, the standing wave, and we'll see how to calculate that energy, and also what that energy exactly is, where it is located, how it delocalizes, and so on and so forth. Okay. So now coming to the next point, which is about the energy. So mechanical energy of a standing wave. Next point. Oscillation energy. Important. Of a standing wave. So first of all, the point we should understand that the standing or stationary wave have a fixed amount of oscillation energy. Because fixed length of string is an oscillation with fixed energy. Unlike a traveling wave, wherein the length of string vibrating is continuously increasing. Hence, a fixed power is being transmitted. That is a counter example. वहाँ पे ऐसा नहीं होता है. It doesn't have a fixed amount of oscillation energy or mechanical energy. This has a fixed amount of energy. So what is happening is in your string, so far the model that we have taken, your source S1 would be somewhere over here at x equal to 0, creating this waves y1, and at a different position, let's say x equal to L, your source S2 would have to be there because it's creating waves in the opposite direction. So the length of the string which is in oscillation, that's a fixed amount of length. So that's first thing. Now the other thing to understand is that the energy that is the oscillation energy, keeps oscillating between potential and kinetic energy. That is elastic potential energy and kinetic energy. And delocalizes. So this point we'll understand in detail, because this is also an important point. So it keeps delocalizing or shifting as it does. So the energy keeps, as it oscillates between potential energy and kinetic energy, the location of where that energy is there, okay, which are the particles possessing maximum energy and which are the particles possessing minimum energy, that also keeps shifting. Okay. So let's understand this with the snapshot pictures. So we'll realize that at some instant, let us say that our string is in this kind of situation. Its shape is like this. At some particular instant of time, say a string is like this, where at the antinodes, so all particles are at extreme position. All particles are at simultaneously at extreme positions. So what is happening in this case is that kinetic energy is zero. And let's say the string is, we're considering the string between this node and this node. So it's a fixed amount of length. So kinetic energy is zero and elastic potential energy is maximum. But where is that elastic energy localized? So as we understood this repeatedly, it's localized where the slope of the string is maximum. So it's localized here. So at an instant when y is maximum, I mean mod y is maximum for all medium particles. The energy, the mechanical energy is in the form of pure elastic potential energy, because kinetic energy is zero. And the particles located at and near the nodes have a high amount of this elastic potential energy, whereas particles near and exactly at antinodes have no or little potential energy. So the energy is localized around the nodes, as you can see. So if this was happening, this is the situation at some t equal to t1, let's say. Now what will happen at an instant? At an instant of time, which is quarter of time period later, all the particles would have reached this kind of position. So at a t equal to t1 plus capital T by 4, okay, would reach this kind of position, where you can see that the speed of the moving particles or the velocity of the moving particles, this antinodal point is rushing down to now go towards the negative mean, negative extreme. So the velocity vectors will look like this. Similarly, this next consecutive antinode opposite in phase with respect to these particles. So at the next instant, the kinetic energy you can see is localized around the antinodes. So the particles located at the antinode have maximum kinetic energy. The particles located at the nodes, of course, have zero kinetic energy, not only at this instant but at all instants. Okay. So the concentration of the energy is now shifted from the nodes to the antinodes, as also the quality of the energy has shifted from pure potential energy to pure kinetic energy. So when the particles at an instant, when all the particles of the medium are simultaneously going through their mean positions, okay, that is y is equal to 0. Okay. The energy of the medium becomes pure kinetic energy. The potential energy becomes 0 because this thing is not at all stretched. It's at the natural horizontal kind of situation. Okay. And kinetic energy is or has a maximum concentration at the antinodes. Whereas it's tending to 0 at the nodes. I mean 0 at the nodes and tending to 0. So just make a note or just a short note or whatever of this point, okay, because it's very important to understand, and then we'll also see the type of questions you can get related to this. Okay, so just make a note of this, guys. Yeah, Sushruta, I'll show the part before this. This is the note about mechanical energy. Okay, so now let's see a numerical question kind of thing based on this. So for the standing wave given by the equation y is equal to 2 is sine kx, sine omega t, where k is equal to 2 pi by lambda, omega is equal to 2 pi f. First of all, express the positions of the nodes and antinodes in terms of lambda. Second, express the equation of oscillation for a particle located at okay, so let us do these many parts first. Then I will come to another important aspect of how to calculate the total energy of oscillation for a certain length of the string. Yes, Somadev, that is correct. Yes, Ganesh, correct. Very good, that's correct. So I'm just working out the first two parts for you people. Sine omega t. Pepper. So you can see that amplitude medium particle is given by this. Therefore, amplitude equal to 2a, that is antinodes for sine kx being plus minus 1. So kx being pi by 2, 3 pi by 2. So these become the position of the nodes, sorry, the antinodes. That's maximum amplitude positions. Similarly, amplitude is equal to 0 for points such that sine kx should become 0. So kx should be 0 pi n pi. So x should be equal to 0 lambda by 2 lambda 3 lambda by 2 n lambda by 2. This will be the general set of coordinates of the nodes. That's the first thing, the nodes and antinodes. Okay, so now let's come to the next thing. We have to find the equation of oscillation for these particular positions. Okay, so just plug them in the equation. Lambda by 6, 5 lambda by 4 and 5 lambda by 2. So you can see that for the second part, substitute x equal to lambda by 6. So this becomes 2a sine k lambda by 6, okay, sine omega t. So that is 2a sine pi by 3 sine omega t. That's root 3a sine omega t. So this becomes the equation of oscillation for that particular point in the string. Okay, so this is the equation of SHM for the particle, for the particular medium particle located at x equal to lambda by 6. So it has an amplitude of root 3a and a frequency of f, or angular frequency of omega. Okay, similarly, you are simultaneously for the B part, substitute x as 5 lambda by 4 instead of lambda by 6. Okay, so next part will be like this. So the point at x equal to 5 lambda by 4 is in fact an anti-node point, as we have seen before. This is the SHM of the particle at x equal to lambda by 6. नहीं समझे वो कोई जरूरी नहीं है कि 2a cos kx हो. That depends on the phase of the this thing, na? The waves which are starting y1 and y2. So it can have generally any phase. The general equation was 2a cos kx plus 5 by 2 sine omega t plus some 5 by 2 like that. So we can select accordingly. So different cases of those phase terms are possible. Okay? The only thing that is assured for a standing wave energy for length we'll discuss about that. Similarly, 5 lambda by 2 you will see is a node point. It is 0. So that's a node, as you already see it in the formula. So nothing surprising about that. This is a node. So 5 lambda by 2. Okay, now we want to find the time at which the wave has maximum potential energy and maximum kinetic energy. So third part. Therefore, a particle velocity of the medium particles is 2a omega sine kx cos omega. Okay. Therefore, kinetic energy is maximum when magnitude of particle velocity is maximum. So that is when cos omega t is plus or minus 1. So omega t is 0 pi that n pi. So time whereas similarly you will see your potential energy is maximum, elastic potential energy is maximum when kinetic energy is zero or particle velocity is zero. So that is when cos omega t is zero. That means omega t, the time will be 1 by 4f, 3 by 4f in general, this type of time. So the general formula for when potential energy is maximum is odd multiple of t by 4 or odd multiple of 1 upon 4f. Whereas the general formula of when kinetic energy is maximum is when T is n by 2 times capital T or n by 2 f. Just make a quick note of this, then we'll discuss one more aspect of this energy before we move on to the next part, which is resonant modes and modal vibrations. Yes, sure. Okay, so this is clear, I hope. Okay, now the next thing we'll see in the same question, see another part of it. Now or let's say another question only, for the wave, the standing wave, want to calculate the total mechanical energy of a section of the string from x equal to 0 to x equal to lambda, oscillating as per the equation given. So a section of the string is between x equal to 0 and x equal to lambda, where of course k only is 2 pi by lambda, and omega is equal to 2 pi f. So we want to find this out. Okay, so let's understand how to work this out. So we can see that given that the position of any particle x at any time t is given by this equation. Okay. The velocity of any particle x as a function of time t, that is nothing but del y by del t. Yeah, I'll verify that. No, there will be a by 4 factor. Let me explain that. Okay. So this will be 2a omega sine kx cos omega. So now for this very thing, okay, let us visualize the string itself between these 2 points, x equal to 0 and x equal to lambda. Now we'll see that from what we had analyzed earlier, nodes were at x equal to 0, lambda by 2 lambda, whereas in this case the antinodes will be at x equal to lambda by 4 and 3 lambda by 4, because we are now considering only for x between 0 and lambda. So we'll only consider this. Okay. So at any instant of time in between, so like this, after some time, when it comes to the negative side, this one comes to the positive side. This is how it is. Okay. So the given section of our string from 0 to lambda has 3 nodes and 2 antinodes. Okay. So anyway, so at any instant like this, if we consider a general particle dx, so when it's over here, for example, is going up like this. So for a section dx of the string, that is from x equal to x to x equal to x plus dx, that section of the string, the kinetic energy as a function of time will become half dm into particle velocity square, where dm will be linear mass density into dx. So the kinetic energy as a function of time, I should write it as a differential kinetic energy. For this string, the kinetic energy become half mu dx into particle velocity, which will become 4a square omega square sine square dx cos square omega. So that kinetic energy is sine square dx cos square omega t. So that particular medium particle which is located at x equal to x, or which is located between x and x plus dx, that particular section of the string has this much kinetic energy as a function of time. So over an oscillation or a cycle, the average kinetic energy of the section dx of the string, that average kinetic energy, when write like this, will be 2 times e square omega square sine square kx into cos square omega t function's average, because we are time averaging it. Understand this, okay? Not averaging it with respect to x. We are averaging over one cycle or one time period. Okay, so we are time averaging it. Now we already seen many times that sine square function and cos square functions averaged over a cycle is half. So this thing averaged over a cycle is nothing but integration of cos square omega t dt from t equal to 0 to t equal to capital T, whole thing divided by capital T. So we don't need to get into this integration again. We've seen it before, that average value of sine square function or cos square function over a cycle or over n number of cycles is half. So the average kinetic energy will equal e square omega square sine square kx for that particular particle. So the average energy, or you can say that the average value of kinetic energy for the whole string, so there's a mu dx also, my mistake, this whole term has a mu dx also, because let's not forget that mu dx part. So therefore the average kinetic energy of the string itself, which is from x equal to 0 to x equal to lambda, because we are considering the string of length lambda here, that average kinetic energy will become e square omega square sine square dx integrated from x equal to 0 to x equal to lambda. Now again you can see that integration of sine square kx dx from x equal to 0 to x equal to lambda, we can write as average value of sine square kx into lambda. So that is going to be lambda by 2. Okay, so no need to do this integration. You know that it will give you lambda by 2. It's also mu somewhere. Got it. So ये जो section है यहाँ पे mu भी रहेगा. That mu dx term was there for the differential kinetic energy. It's mu dx. So this will become from this understanding, it will become mu a square omega square into integration of this part. So that's the average value of sine square function half into the this thing over which we are doing, the limits over which we are doing 0 to lambda. Okay. So therefore the total energy will become average kinetic energy plus average potential energy, which we will just take as 2 times average kinetic energy, because the average potential energy should be equal to the average kinetic energy. Even though they are maximizing at different times, they are interchanging, but because of the symmetry nature, okay, so the total energy of oscillation of a section of length lambda of the string will become half, sorry, double of this now. So become lambda into mu into a square omega square. So if you think of it logically, you can understand that it is m, that is the mass of that section of the string, into maximum amplitude square omega square by 4, where maximum amplitude is the amplitude of the this thing. So first of all, m is the mass of the string of length lambda, or mu l, where the length of that section get taken as lambda, and E max was equal to 2a from that equation above. So that energy is 1/4 of m. This is amplitude of antinode. So you don't need to memorize this formula here. Okay. In fact, this formula will become more important in the context of resonant modes of a vibrating string, which we will discuss about next. But just this process I want you to once again understand, how we calculate the average kinetic energy of that particle time averaged of section dx. Then we integrate that for the section of the string going from x equal to 0 to whatever length n. So that gives you the average kinetic energy of that section of the string, time averaged kinetic energy of that section of the string. And then we just use simple logic that the average kinetic energy will be equal to the average elastic potential energy, and from that, okay, so just make a note of this, people. Yeah, Bhaumic part is the average kinetic energy is equal to the average potential energy, because ultimately it is a set of particles in SHM. So there is that symmetry of the two types of energy in SHM. On correction here, this should be 2, but then this step is correct. When you put the time average, come out to be half only. Okay, people. So hope this derivation is clear. As I told you, you don't strictly need to memorize this formula. You will understand how to logically apply it in a situation where, I mean, we'll revisit this situation. Here we are taking the example where x is between 0 and lambda just. Okay. So we are taking that section of the string which is between the first and the third node. Okay. And in between there are two antinodes also. But we'll generalize that more later. So now let's come to the final section of this chapter, transverse vibrations of a string, and that is the resonant modes of vibration of a string which has fixed boundaries. For a string of finite length, not infinite length, but finite length, say L, between two boundaries at x equal to 0 and x equal to L. So this is the final section. So don't worry about the term resonant mode yet, we'll understand that. So the first case we'll take is when both boundaries are fixed, or what we call rigid boundaries. So we have a string of length L, and both the ends of the string are rigid boundaries. And of course, the string has a tension T and a linear mass density mu. Now let us understand how the string can vibrate naturally. Okay. So if the string vibrates naturally, or in what we call a natural resonant mode of oscillation, okay, it should be, or it should form a standing wave pattern with both ends, that is fixed boundaries, nodes. So in other words, but the physically or at an experimental level, you can understand that if I give this string some oscillation energy, then a natural way in which it will oscillate will be a standing wave pattern, such that this boundary and this point boundary are nodes. So let us see what kind of standing waves of that are possible. So we'll understand the what is called the fundamental mode of the string's oscillation. So in that fundamental mode, what will happen is there should be least number of nodes and antinodes possible. So if x equal to 0 is a nodal point and x equal to whatever this length of the string is L, that's also a nodal point. But there are minimum number of nodes and antinodes. So the midpoint should be an antinode. The midpoint should be an antinode. Yeah, Sudhir, you can take down the whole thing later. Now pay attention to what I'm explaining over here. So it should vibrate in this kind of a mode. So at an experimental level, you'll understand that if I were to pluck the string just at its proper midpoint, then wherever I'm plucking the string, where I'm holding it and actually displacing it, that point should have maximum displacement or maximum amplitude. Whereas the fixed boundaries at x equal to 0 and x equal to L are obviously not going to be allowed to displace because they are rigid boundaries. So they are going to have to be the next two consecutive nodes with respect to A, the antinode at the midpoint. So in such a situation, so when I pluck the string like this and release it, it will vibrate at a certain natural frequency. So that natural frequency for this particular mode is called the fundamental mode of vibration. So in the fundamental mode, the string vibrates at a fundamental frequency which we denote with the symbol F0, such that the length of the string now is the distance between node and node, consecutive node and node. So it is lambda by 2. This is a node. This is the next consecutive antinode. So this length L is becoming the distance between two consecutive nodes. So the wavelength of oscillation has to be equal to 2L. Therefore, the frequency of oscillation has to be equal to 1 by 2L square root T by mu, where T is the tension and mu is the linear mass density. So this becomes the formula for the fundamental frequency of oscillation. Okay, now in a bit of time you'll understand why this is called the fundamental mode. Okay, but first, just you can take a brief note of this part. Okay, students, I'll just wait another minute or so for others to join in. And then we finish this part and conclude the lecture. No, you have another lecture at 11, but just want to conclude this part. Just give it 2 minutes for some of the students to join back. So in the meantime, you just go through this section, okay, and note down from this part. Okay, so anyhow, let's just understand about the fundamental mode. So when the string is vibrating in the fundamental mode of vibration, okay, what we mean by fundamental mode of vibration is that it's that mode in which the number of nodes and antinodes is the minimum possible. So you can think of fundamental mode. We'll talk about a more elaborate definition later, but right now just think of the fundamental mode such that the number of nodes or antinodes is minimum in the fundamental mode. At an experimental level, you can say that we would have achieved this when we just plug the midpoint of the string, okay, and cause it to become an antinode. And this is how the shape of the string looks. So if this is how the shape of the string looks, that means the fixed boundaries, which are a distance L apart, are becoming consecutive nodes. Okay, so that is why this is becoming lambda by 2. Because the fixed boundaries, which are L apart, are consecutive nodes. So the distance between consecutive nodes is lambda by 2. So once I know this is lambda by 2, I know the frequency will become this, because the relation is f, f lambda should be equal to square root p by nu. That is the physical property of the string. The relationship between wavelength, frequency, tension, and linear mass density. Now, the next possible mode which can happen, that is the fundamental mode is where the number of antinodes or the number of nodes is minimum. Now, the next lowest possible number of nodes and antinodes, when that happens, we call the mode of vibration as the first overtone mode. Okay, so the terminology is important here. The first overtone mode. Yeah, I understand. No problem. Okay. So the first overtone mode of vibration will be that mode of vibration where it's the next lowest number of nodes and antinodes possible in this mode. Fundamental mode was one where there was the lowest, absolute lowest. The next lowest number of nodes and antinodes When that occurs, we call it the first overtone of vibration. And the frequency of this first overtone is denoted by the symbol F1. So we said at frequency F1, whereas the fundamental was F0. So when this happens, the midpoint of the string also becomes a node. So we have 3 nodes and 2 antinodes. That is the mode of vibration. The string oscillates in this kind of manner. So now you can see the distance between consecutive nodes becomes half the length of the string. So this distance, lambda by 2, in fact half the length of it. The first overtone mode has 3 antinodes and 2 antinodes and 3 nodes. So in this mode, what is happening is that lambda is becoming equal to lambda by 2 is equal to L by 2. So the first overtone has a frequency of 1 by L square root P by nu. Or more importantly, the first overtone mode in which the string can vibrate will have a frequency which, if you compare with the fundamental mode, it will become twice the fundamental. So I just give you the comparison of the 2 modes of vibration, then you will understand this in more detail. The first overtone mode is where the shape of the string becomes such that you have another node in between the 2 fixed boundaries. So fundamental mode where we have the minimum possible number of nodes and antinodes. So the fixed boundaries are 2 consecutive nodes. First overtone is the situation where we have the next minimum number of nodes and antinodes. So midpoint becomes another node. So we have 3 nodes plus 2 antinodes. So the 3 nodes are the boundaries or the ends of the string plus 1 midpoint. Those become the nodes. And the shape of the string looks like this. It looks like 2 loops of vibration. Alright. Now, like that, you realize that the second overtone is the next possible situation. So in the second overtone mode of vibration, we will have 4 nodes plus 3 antinodes. The shape of the string will look like it is now divided into 3 loops. This will be one boundary. vibrating like this. As you can see, this mode of vibration, the frequency is denoted by the symbol F2. So this lambda by 2 becomes L by 3 because there are 3 equal bits like this. So lambda by 2 is equal to L by 3, or lambda becomes 2L by 3. So the frequency becomes 1 by lambda, that is 2L by 3 square root T by mu, or it becomes 3 by 2L square root T by mu. So if you compare it with the fundamental frequency, you can see that the frequency becomes 3 times the fundamental. Okay. And this is how this series continues. So you have the fundamental frequency 1 by 2L square root T by mu. The first overtone becomes 2 times F0. The second overtone becomes 3 times F0. The third overtone becomes 4 times F0. And like that, what we call the nth overtone becomes n plus 1 F0. So this becomes the formula of the series of harmonics. Okay. This whole thing is called the harmonic series, okay, or modes of vibration. Okay, or harmonic modes. Okay. Now, in this terminology, which is important, this is called nth overtone mode. So F0 is called the fundamental. F1 is called the first overtone. F2 is called the second overtone. Like that. Whereas, also important, this last point we will conclude. We have this formula. Okay. So for example, F1 is 2F0, F3 will become 4F0, like that. Okay. So in this is called the harmonic. So this is called the n plus 1th harmonic of fundamental. Okay. So the harmonic is just basically the number multiplied by fundamental. So the harmonic is the multiple of fundamental. So in language, we will say over here that first overtone mode has a frequency which is equal to second harmonic of the fundamental mode, or the fundamental frequency. Like that, the second overtone mode has a frequency equal to third harmonic, and so on and so forth. So the nth overtone mode has a frequency equal to the n plus 1th multiple or harmonic of the fundamental frequency. Okay. So these are some of the key points you have to understand about the resonant modes of vibration of a string fixed at two boundaries. Okay. So I'm going to conclude here, people, today, because I have a lecture also coming up. I would have liked to discuss a couple of more things, but no problem. We'll start the next lecture with a recap of this and discussion of few more points. But actually, this will be sufficient for you to complete at least the HC Verma level of questions of standing waves. So just make sure you review the notes at least, if possible, the recording also, and you understand this relationship. The fundamental frequency is given by this formula, and from this now the nth overtone is given by n plus 1 times the fundamental. So the formula of the nth overtone mode becomes n plus 1 divided by 2l square root t by mu. This is another way to express the nth overtone mode. But of course, this comes later. Here we understand the fundamental, the first overtone, then the second overtone, then we generalize it. Okay, so that's it for today, people. Thanks for attending, and let's continue with the problems. Also, next lecture we will have some time set aside for discussion of doubts.